Okay, so here is another example of an algebraic proof of how to show that this is equivalent to that. Okay. Again, I mean, like we have done a slightly fancier version, so we don't need to worry about this. But the idea would be what? To see both the sides, and basically, I think it would be easier to go from what? From the left-hand side to the right-hand side. Okay. So what will you do? You have a x or and y, right? Sorry, x or negative y and y. Yeah. So you will distribute. So once you distribute, you'll get what? X. Well, here we are using commutativity. You don't need to. You can just basically say y and x or y and negative y. Y and negative y, it's always what? F, right? It's one of those laws, right? It's a complement identity. And if you have anything, so we have y and x or f, then it will basically be y and f, right? Because p or false is p, because it will depend on p, what the truth value of p is, right? So you get this, and which is same as this one, right? So this is an example of yeah, you can do this problem later. All right, next thing I want to talk about is rule of inferences. So what is the rule of inference? What is the idea behind it? So in a logical argument expression of form P1 and P2 and P3 and P4 and P5 and Pn implies Q is a general form of an argument. Okay. So the idea is that you'll have a bunch of P1, P2, P3, P4, P5, and of this implying Q, this is called an argument. Okay. Where again, what P1, P2, P3, Pn are called premises, and Q is called conclusion. All right. Does that make sense? Now, when all the premises are true, the argument is said to be valid if this ensures that A, this whole statement is true. Yeah. If this whole statement is false, then basically, then the argument is invalid. Yeah. It's a very natural generalization of what we have done so far. We have a bunch of statements, P1, P2, P3, P4, and we assume that all of them is true. And then we are asking, does P1, P2, Pn being true implies Q is true or not? If it is true, then we say that this argument system is a valid argument. Otherwise, it's not a valid argument. Is that okay? So now, valid argument, if it is can be proven by a series of axioms, that is a theorem. All right. So theorem is basically something which can be proven by the series of axioms. We'll do a problem so that it will become very clear to you what is happening. And a lemma is a simple theorem. It's a baby theorem. That's what lemma is. Very, very straightforward result. And corollary is something which is comes as an easy consequence of a theorem. Okay. Again, we don't need to worry about these names yet. Let's try to do some problem. Okay. So what are the rules of inferences? So these are all the rules of inferences. Unfortunately, these are Latin names for it. We are not the first ones to invent it. So otherwise, we could have called it whatever we want. So one is called modus ponens. So what is the idea behind the modus ponens? Modus ponens simply says, if you are given P implies Q, and you're given P, that means what? Q. Therefore, Q. What is the meaning of this? Suppose P implies Q is true, and P is true. That means what? Q must be true. Is it? No, it's not. Doesn't mean that Q is true. It means the output will depend on what? The value of Q. Is that okay? If this was always true, then the answer in here would have been what? Just P. Yeah? Does that make sense to you? Yeah? So here we are saying that Q. Okay? So that means what? P implies Q, P, and therefore Q. That means what? This is exactly same as saying Q. Okay? Whether Q is true or false. Right? So this is modus ponens. All right? Then there is law of syllogism, which is basically P implies Q, and you have Q implies R. Then simply it is what? P implies R. Okay? So this is called law of syllogism. Yeah. Another one is the rule of modus tollens. Modus tollens simply is P implies Q and negative Q. This means what? Not okay. So these are the laws of okay. All right. Now, before I go further, there's something I did not talk about is the following. I should quickly talk about those things. Namely, again, these are from laws of logic. So if I give you a statement, P implies Q. So if you're given P implies Q, for this statement, there is so-called contrapositive of the statement. Okay. Contrapositive of this statement is negative Q implies negative P. Okay. Yeah, given a statement, P implies Q, there's a contrapositive of that statement, which is negative Q implies negative P. There is the converse of this statement, which is same as what? Q implies. Yeah. It's like saying, okay, let me have a funny example. If it is a monkey, it can fly. Does it mean that if it can fly, it's a monkey? That is what the converse of this statement. Yeah. Yeah. If A implies B, does B implies A? All right. And inverse is basically going to be so we have P implies Q, negative Q implies negative P, and then there is so-called inverse, which will be essentially negative P implies negative Q. Okay. So given a statement, these are the corresponding statements associated with it. All right. In fact, you can see quickly P implies Q is actually equivalent to negative Q implies negative P. These two statements are equivalent. Okay. So a statement and its contrapositive are equivalent statement. Is that okay? Yeah. You can check that. You'll say, oh, how do I check it? Well, one way is use truth table, or you can do it directly. P implies Q. What is that equivalent to? We agree that is same as negative P or Q. Yeah. Is it not same as Q? Is this same equivalent to? Okay, so I have what? Negative P or Q, right? Do you agree? Now, these two statements are equivalent, right? This is my implication reduction. Okay, now let's see. What do I want? I want negative Q first, right? So can I change this as Q or negative P? Yeah, commutativity. Let's just write it down. Commutative. And then I can write Q as negative of negative Q. Right? Let me see. What is that name of that law there? Yeah. So double negation, right? So let's just write that down. Double negation. And then voila, we are done. This implies this now again by implication reduction is going to be what? This is going to be negative Q implies negative P. We're done. Isn't it? Yeah. You have what? You have the following, right? Box, negative box or triangle is equivalent to box implies triangle. Yeah? Whatever is inside that box doesn't matter. Yeah. So this is the algebraic proof of this statement. So a statement and its contrapositive are equivalent. Yeah. Would be a nice exercise just for home to check. What about converse and inverse? Are they equivalent? What do you think? The answer is of course. All right. So now let's go back to the reason why I talked about that is because I wanted to talk about modus tollens. So modus tollens is what? Negative Q and P implies Q and negative Q implies. So let's look at this statement, okay? And let's see how it follows from modus ponens. Or so P implies Q, and we have negative Q. Okay, let's see what is the outcome of that. So the way generally this written is basically it's written line by line like this. Now, so can I add to this statement? Can I? So let me write this one. This is 2. These are given to me. Okay. Now third statement. Can I write negative Q implies negative P? Yeah. What is the justification? Contra positive. Okay. So some of these laws are not written there because these are equivalent statements. The statements which are logically equivalent can automatically be put. You don't need to need laws for this. Is that okay? Yeah. For everything else, there's a law. Yeah, inference law. Okay, because inference are weaker than logical equivalence. Logical equivalence means two things are exactly the same. Yeah, inference simply means what A implies B. Doesn't mean they are equal, right? For example, you can say that if it is a bird, well, if it flies, it's a bird. Yeah, but it's a bird doesn't mean it flies, for example. Yeah, so inference is like P implies Q. But in logical equivalence, P and Q are same things. Okay, so logical inference is logical equivalence is much stronger statement than inference. Right? Rules of inference basically only go anyway. Okay, so we now have. So now what do we have? We have negative Q. We have negative P implies Q. Look at this law. Yeah, P implies Q, and then we have negative Q. This implies what? P, right? Isn't it? Like so, modus tollens is exactly same as modus ponens, of course, with a contrapositive included. Okay. Well, you don't need to worry so much about it. Let's look at some more problems. Okay. So these are the rules you're going to use. Let me just mention these rules again. P implies Q, and if P, this is same as Q. Okay. Therefore, Q. This is modus ponens. We talked about modus tollens. Conjunction is if P is true and Q is true, that means what? P and Q is true, isn't it? Yeah, obviously, right? Isn't it? If P is true, Q is true, then and of them is going to be true. So this is conjunction law. Now, disjunctive syllogism. If P or Q, yeah, if you have P or Q, if negative P is true, that means if P is false, Q, basically what will happen? Then the value of this will depend on what Q is, right? Do you agree? So this gives me Q. Similarly here, conjunctive simplification. If P and Q is true, then I can write Q or P as well. Does it make sense to you? And then there's a disjunct amplification. Okay, so this is law of syllogism we already talked about. Let's do one problem on laws of inference. So here, problem 1. P and Q. P implies Q implies R. Okay, therefore R. Is this statement, the question is this statement valid? So we want to basically see P and Q, P implies Q as R, we want to basically see if this statement is valid. Okay. So how do we go about it? So that's the idea. So all right. So let's see how do we approach such a problem. So again, therefore R, this statement is valid or not. That's what we are checking. It may not be valid at all. Okay. Let's check. So how do we go about it? So first of all, let's write it down. 1, P and Q. P implies Q implies R. Let's see whether R is true or not. Okay. Now, so how do we go about it? So do you see the way to approach this problem will be somehow to isolate R, right? How do we get to R? Okay. Notice the following. P and Q. Therefore, P, we agree. Isn't it? What is that law called? It's called conjunction. So P and Q, therefore P, right? From the first one and conjunction. And that's why it's important to name them, because you know why? Because once you start doing this way, you will get a complete handle of it. Okay, one and conjunction. Now, if you have P and your P implies something, therefore we get what? Q implies R. What law is that? What law am I writing? Let's say box implies triangle, box, therefore triangle. Yeah, it's one of those laws, right? Let's go back and see what law is this. We have what? We have P implies Q and Q. Therefore, what is Q? Q. Yeah, therefore Q. Not true, but therefore Q, right? So we get here what? Let's go back to our problem. Therefore, we get this. Again, what can we say? 3. And where are we using modus ponens? 3 and 2 and what? Modus ponens. Do you agree with that? Yeah. Yeah, so next time I will bring you the table so that you can keep the table on the side. We'll try to do some problems in the next class, early next class on some of these as well. Please digest this. This is very important, huh? Digest this. I don't want to like overfeed you today, but next class, so we can have not have this in the quiz, but try to digest this as much as you can. We can just have until laws of logic, just before the rules of inference for the quiz, but try to get to this thing and we can talk further. Okay, so now I have what? I have 5. Now notice the following, interesting. P and Q again gives me what? Q as well, right? Why again? 1 and conjunction. Now I have Q and Q implies R. Therefore, what do I get? R. What is that rule called? Modus ponens again. 5 and 4 and modus ponens. There we go. Voila. Yeah, does it make sense? So this is how we'll apply the rules of inference, right? So therefore, what is the upshot of this? We have shown that P and Q is true, and if P implies Q implies R, therefore, this statement that these implies R is a valid statement. Okay. Now, let's look at one more problem before we stop. Problem 2. So we have P implies Q, and we have R implies S, and we have P or R. And the answer, what we are looking for is Q or S. What about this guy?